Hello, in this video we are going to be looking at whether series converge or diverge, and in particular we're going to be looking at the nth term test for divergence, the p-series test, and the integral test. For our first activity, let's assume that the series, the sum from k equals 1 to infinity of a sub k, converges to L. It converges so we know it has a finite sum, and that finite value we're calling L. First question, what is the nth partial sum of the series? So the nth partial sum is the sum of the first n terms. So that looks like the first term plus the second term plus the third term plus ... all the way up to the nth term plus a sub n. And the term that comes right before the nth term has a subscript of n minus 1. So a1 plus a2 plus a3 plus ... plus a sub n minus 1 plus a sub n. Part B, what is the n minus first partial sum of the series? So now we're going to add up the terms until we get to the n minus first term. So s sub n minus 1 would be a sub 1 plus a sub 2 plus a sub 3 plus ... all the way until we get to a sub n minus 1, and then we stop. Part C, what is the difference between the nth partial sum and the n minus first partial sum? The difference between, so we're going to subtract. We're going to look at what is s sub n minus s sub n minus 1. Well, here I'm going to have, if I'm subtracting, I have a1 minus a1, and then a2 minus a2, a3 minus a3, and so on, all the way up to a sub n minus 1 minus a sub n minus 1. All we're going to have left is this last term here. So that's just going to equal a sub n, the nth term. Since we're assuming that the sum of the series is L, what does that tell us about the limit as n approaches infinity of s sub n? What does that tell us about the limit as n approaches infinity of s sub n minus 1? Well, s sub n is the nth partial sum. We're taking the limit as n approaches infinity. So we're approaching like the infinite sum here, which is the actual sum, which is L. So if we find this limit, just kind of using substitution, we're going to get L. That limit is equal to L. And likewise, s sub n minus 1, if n is approaching infinity, then we're approaching the infinite partial sum. So it's also just going to equal L. Part E, combine the results of the previous two parts of this activity to determine the limit of a sub n as n approaches infinity. Well, remember we had the fact that s sub n minus s sub n minus 1 was equal to a sub n. So let's take the limit of both sides. The limit of s sub n as n approaches infinity minus the limit of s sub n minus 1 as n approaches infinity equals the limit of a sub n as n approaches infinity. But the limit of s sub n as n approaches infinity was L minus, and the limit of s sub n minus 1 was also L. L minus L equals 0. Therefore, the limit of a sub n as n approaches infinity must equal 0. If the series sum of a sub k from k equals 1 to infinity converges and has a sum of L, what does this fact tell us about the sequence for a sub n? Well, since the limit of a sub n as n approaches infinity equals 0, we can say that the sequence converges to 0. So this leads us to our next theorem, the nth term test for divergence. If the series a sub n converges, then the limit of the sequence for a sub n as n approaches infinity must equal 0. Now the contrapositive of that statement would say, if the limit of the sequence for a sub n does not converge to 0, then the series does not converge. In other words, it diverges. Okay, so this is a really important theorem that we're going to be using quite a bit. Note that the nth term test is a test for divergence only. You cannot use the nth term test to conclude that a series converges. You can only show that a series diverges. If the limit of a sub n as n approaches infinity is 0, that tells us nothing about the convergence or divergence of the series. It might converge, it might diverge. We don't know. But if the nth term is not approaching 0 as n approaches infinity, we can conclude that our series diverges. Determine whether the series converges or diverges. So it's not a bad idea to always try the nth term test as a starting point, unless you look at your series and right away you recognize it as one of our special types, like a geometric series, for example. So part A is a geometric series. I can use the geometric series test by looking at the value of r, that common ratio. In this case, r is 2. The absolute value of r is greater than 1. So since absolute value of 2 is greater than 1, therefore my series diverges by the geometric series test. Part B, we have the sum from n equals 1 to infinity, n factorial over 2 times n factorial plus 1. So I'm going to see what happens with the nth term test. And I do that by taking the limit of the nth term, so n factorial over 2 times n factorial plus 1, as n approaches infinity. This limit is equal to 1/2. 1/2 is not 0. So this series can't possibly converge. The only way a series can converge is if the limit of the nth term as n approaches infinity is 0. And that is not the case here. So therefore, our series diverges by the nth term test. The next one, if we try the nth term test, what is the limit as n approaches infinity of 1 over n minus 1 over n plus 1? Well, that limit is 0 minus 0 or 0. If you get 0, that tells you nothing about the convergence or divergence. It might converge, it might diverge. So this was not helpful at all. We have to try something else. Well, this looks like it's in the form of a telescoping series. So let's expand and see what happens. When n equals 1, we have 1 minus 1/2. Plus, when n equals 2, we get 1/2 minus 1/3. Plus, when n is 3, we get 1/3 minus 1/4. Plus, and so forth, all the way up until the nth term where we have 1 over n minus 1 over n plus 1. So all of these inside terms end up canceling out. And this sum, the infinite sum, is just equal to the limit as n approaches infinity of 1 minus 1 over n plus 1. And that limit is equal to 1 minus 0 or 1. Therefore, our series converges. Next, part D. We want the sum from k equals 1 to infinity, k over k plus 1. So let's take the limit of the nth term. The limit of k over k plus 1 as n approaches infinity, actually as k approaches infinity in this case, is equal to 1. The limit of the nth term as n approaches infinity is equal to 1, which is not 0. Therefore, this series diverges by the nth term test. The next one, if we try the limit of the nth term, so negative 1 to the n, or we can stick with k, or I'm just going to change it to an n, as n approaches infinity, well, this limit does not exist. That limit does not exist. This series just keeps alternating. It's minus 1 plus 1, minus 1 plus 1, minus 1 plus 1, so it diverges. But note here, we did not get 0. If the limit is not 0, then we know the series diverges. So we can say diverges by the nth term test. So we've looked at the nth term test for divergence. Next, we're going to look at the integral test. Suppose we have a function f of x that's positive, so it's above the x-axis, it's continuous, and it's decreasing for all x greater than or equal to 1. And a sub n is the function f of n. If we consider a right-hand Riemann sum, we can see in the diagram here that the Riemann sum is going to be an under approximation of the actual area under the curve. But the Riemann sum, we're adding up a bunch of areas of rectangles. So this represents a series. If it's a right-hand sum, then the first height happens here when x is 2. So that's going to be f of 2 is the height right here. This value is f of 2 is the height of that first rectangle, times the width, which is just 1. And then we have f of 3 is the height of our next rectangle. And so it's just the height times the width of 1. So really what we're going to end up adding is f of 2 plus f of 3 plus f of 4 and so on, which is what we see is happening over here. So we're adding up f of 2, f of 3, f of 4 plus dot 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 all the way up until we get to the end here, and this last height is f of n. We can write this in sigma notation. If we say it's the sum of f of I, starting with, we want f of 2 to be our first value. So an index of 2, from I equals 2 up to n, because we stop when we get to f of n. And because this Riemann sum is an under approximation, we know it's going to be less than or equal to the actual area under the curve, or the integral from 1 to n of f of x dx. Now, if we consider that same function, so it's still positive, continuous, decreasing, but this time we look at a left-hand Riemann sum, our first height of our rectangle is now f of 1. And then the next height for the second rectangle, f of 2, and so on. And since we're using a left-hand sum, the last height isn't f of n, it's f of n minus 1. So we have this series here, because the width of each rectangle is 1, essentially we're just adding up these heights. So that's the series, index starting at 1, ending at n minus 1. And this left-hand Riemann sum is giving us an over approximation, so we know it's going to be larger than the actual area under the curve. The area under the curve we can represent with the integral of f of x from 1 to n. So we have the actual area here in the middle. The right-hand sum is an under approximation. The left-hand Riemann sum is an over approximation. So the actual area is somewhere in between the right-hand Riemann sum and the left-hand Riemann sum. And now we're going to substitute, instead of right-hand Riemann sum, we're going to put it in this sigma notation here. The actual area, we're using our integral notation. The right-hand Riemann sum, we were able to write in sigma notation. Now this right-hand Riemann sum over here, the sum from I equals 2 to n of f of I, is the nth partial sum just without the first term, since our index starts at 2. So we can simply call that s sub n minus f of 1. And then on the right-hand side, here we have the sum going from I equals 1 to n minus 1. That's the n minus first partial sum, so s sub n minus 1. And then our actual area is our integral from 1 to n, f of x dx. So case 1, let's suppose that the integral converges. It converges, it has a finite value, and we're going to call that value L. So I can replace the integral in the middle of this inequality with an L. So then we have s sub n minus f of 1 is less than or equal to L, which is less than or equal to s sub n minus 1. So the sequence for s sub n, this sequence of partial sums, is bounded and monotonic. it's less than or equal to L plus f of 1, so it's bounded above, and it's bounded below. We could say it's bounded below by 0. So it's bounded, and it's monotonic because we keep adding more and more and more positive terms to it. Therefore, the sequence of partial sums converges. And if the sequence of partial sums converges, then our series converges. Okay, so if we have this integral from 1 to infinity f of x dx converging, then we automatically have our series converging as well. Now, case 2, what if our integral diverges instead? Well, we have this n minus first partial sum greater than the integral. And if the integral diverges and s sub n minus 1 is greater than something that diverges, then it must also be divergent. And if the sequence of partial sums diverges, then our series also diverges. Which leads us to our theorem for the integral test. Suppose f is a continuous positive decreasing function on some interval starting at c and going all the way out to infinity, and we have a sub n equals some function of n. So a sub n just represents our nth term. If that integral from c to infinity of f of x dx converges, then our series for a sub n also converges. If that integral diverges, then our series diverges. And the note at the bottom, just because the integral converges to some value doesn't mean that the series converges to the same value. They'll both converge, but not necessarily to the same value. And we wouldn't expect them to converge to the same value. If you go back and look at the graph, the Riemann sum was not exactly equal to the integral. Let's look at an example to see how we can use this integral test. Determine whether the series n equals 1 to infinity of n over n squared plus 1 converges or diverges. So there are certain conditions that have to be met before you can use the integral test. Our function has to be continuous. So this function is continuous. It has to be positive. This function is positive. It's above the x-axis. And it has to be decreasing. Well, this function isn't always decreasing, but at some point, we'll just say here at 1, at some point thereafter, yes, it is always decreasing. So the integral test will apply to this particular series. So what we do is we take our nth term and we just convert it into a function of x. So that's where we're getting the f of x equals x over x squared plus 1. Just change your n's to x's so that we have a function of x. Now we're going to find the integral of f of x. So the integral of x over x squared plus 1 from 1 to infinity. Find that integral, x over x squared plus 1 dx from 1 to infinity. This is an improper integral, but we know how to evaluate improper integrals. We take the limit as b approaches infinity, integral from 1 to b of x over x squared plus 1 dx. Okay, so we have limit as b approaches infinity. Now this integral we can do using u substitution. I'll let my u equal x squared plus 1. My du is 2x dx. So I need the 1/2 to compensate for not having the 2 with the x. And then it's du over u. So that's natural log absolute value of my u. My u is the x squared plus 1. Since that's positive, I can drop the absolute value and just use parentheses. So there's my integral. I'm going from 1 to b as b approaches infinity. So I have limit b approaches infinity of, and then we sub in our upper limit, so 1/2 ln b squared plus 1 minus 1/2 ln of 1 squared plus 1, or 2. Now as b approaches infinity, the natural log of infinity squared plus 1, natural log of infinity is infinity, so this diverges. This integral diverges. And if the integral diverges according to the integral test, then our series diverges. So the integral diverges, therefore our series n over n squared plus 1 also diverges by the integral test. Let's look at another example. So now we have this series from n equals 1 to infinity of 1 over n squared plus 1. If we think of the nth term as our function, 1 over x squared plus 1, and we check the graph, we can see that starting at 0, this function is positive, it's above the x-axis, it's continuous, and it's decreasing. So the integral test will apply. So we're going to find the integral from 1 to infinity of 1 over x squared plus 1 dx. If this integral converges, our series converges. If this integral diverges, our series diverges. This is an improper integral, so we need to take the limit as b approaches infinity from 1 to b, 1 over x squared plus 1 dx. And this is the derivative of arctan x. So the integral 1 over x squared plus 1 is arctan x. So we have limit as b approaches infinity, arctan x from 1 to b, or limit as b approaches infinity, arctan b minus arctan of 1. The arctan of b as b approaches infinity is pi over 2. Think about the graph of arctan. We've got a horizontal asymptote at pi over 2 and then one at negative pi over 2. So as we approach infinity, arctan of b approaches pi over 2 minus arctan of 1. The arctan of 1 is pi over 4. Pi over 2 minus pi over 4 is pi over 4. Pi over 4 is finite, so that tells us our integral converges. Our integral converges. And if our integral converges, then our series converges. So therefore, the series from n equals 1 to infinity, 1 over n squared plus 1, also converges. It doesn't necessarily converge to pi over 4, but it does converge. And that brings us to our final test for today's lesson, the p-series test. We've looked at this before when we talked about improper integrals. For what values of p does the series sum from n equals 1 to infinity of 1 over n to the p converge? So case 1, let's consider if p is equal to 1. If p is equal to 1, then we can think of this as the nth term as 1 over x, if we want to rewrite it as a function, 1 over x. So if we think about the graph of 1 over x, after x equals 0, to the right of x equals 0, we have a function that is positive, continuous, and decreasing. So the integral test does apply. We would set up our integral going from 1 to infinity for 1 over x dx. This is an improper integral, so we use limits. Take the limit as b approaches infinity, integral 1 to b, 1 over x dx. Well, the antiderivative of 1 over x is ln x. So we have limit as b approaches infinity, ln, absolute value of x, from 1 to b. So we get limit as b approaches infinity, ln b minus ln 1. The natural log of 1 is 0, so that just drops out. And the natural log of infinity is infinity. So this integral diverges. And if the integral diverges, then the series diverges. So when p equals 1, the series diverges by the integral test. Okay, so that's if p equals 1. Now, what about the case where p is between 0 and 1? Here, when we integrate, we can think of this as x to the power negative p dx, and then use our power rule for integration. So we're going to get the limit as t approaches infinity. We're going to add 1 to our exponent, so we get x to the 1 minus p, and then we divide by the new exponent, 1 minus p, from 1 to t. So that gives us limit as t approaches infinity of, now the t is going in for the x. So we get t to the power 1 minus p divided by 1 minus p minus, and then we put 1 in for the x, so we get 1 over 1 minus p. As t approaches infinity, now remember p is between 0 and 1. So 1 minus p is positive. 1 minus p is positive. So as t approaches infinity, I have an infinitely large number raised to a positive exponent. This whole term right here is going to approach infinity. And infinity minus this constant term right here is going to still be infinity. So this integral diverges. If p is between 0 and 1, the integral diverges. And if the integral diverges, the series diverges. Okay, so for p between 0 and 1, the series diverges by the integral test. And case 3, what happens if p is greater than 1? So we have limit as t approaches infinity. If p is greater than 1, we still have a function that's positive, continuous, and decreasing, so we can use the integral test. Now I'm integrating 1 over x to the p, which again becomes x to the power negative p, and we'll use our power rule. So we get limit as t approaches infinity, x to the power negative p plus 1, or 1 minus p, divided by the new power from 1 to t. And evaluating that, we get limit t approaches infinity of t to the 1 minus p over 1 minus p minus 1 to the 1 minus p over 1 minus p. Now p is greater than 1, so that means t has a negative exponent. So t is an infinitely large number, but it has a negative exponent, so it's actually infinitely large in the denominator. So we have this first term approaching 0, and then minus 1 over 1 minus p is a constant. So this integral is equal to negative 1 over 1 minus p, which is finite, so the integral converges. And if the integral converges, then our series converges. So we have, for p greater than 1, our series converges by the integral test. Okay, so our p-series test says the p-series, the sum from n equals 1 to infinity of 1 over n to the p, is convergent if p is greater than 1 and divergent if p is less than 1. It says p is less than 1, but p does also have to be greater than 0. Otherwise, we don't have a p-series. So this series right here is called a p-series. So p has to be greater than 0. And our p-series will converge whenever p is greater than 1. So some examples of where we might use our p-series test, if we want to see whether the following series converge or diverge, they're all p-series. This first one is in the form of 1 over n to the power 1. This one diverges since p is not greater than 1. So it diverges by the p-series test. This series actually has a special name. We're going to see this one pop up quite a bit. This is called the harmonic series. and the harmonic series diverges. Number 2, we can rewrite this. Instead of 1 over the cube root of n squared, we can write it as 1 over n to the power 2/3. This is a p-series, as the power of n is greater than 0, but it's less than 1. So this p-series diverges. This diverges by the p-series test. And the last one we can rewrite as the sum from n equals 1 to infinity of 1 over n to the power, so it's the square root of n cubed, that's n to the power 3 over 2. 3 over 2 is 1.5, and that's bigger than 1. So this series converges by the p-series test. So to recap, we looked at the nth term test for divergence, which can only tell us when a series diverges. And we looked at the integral test, which we can only use when the nth term is positive, continuous, and decreasing. And then we looked at the p-series test, which we can only use when we have a p-series.